Hello, I'm Beth Dickey of the NASA Headquarters Office of Public Affairs. Welcome to the Leading Edge, where we take an in-depth look at aeronautics problems that NASA is working to solve through its own research initiatives or in collaboration with others. Today's topic is Automatic Dependent Surveillance Broadcast, or ADS-B, the next generation in airborne surveillance and cockpit avionics. Instead of relying on radar, Adsb uses Global Positioning System satellite information to give pilots and air traffic controllers highly accurate traffic data, as well as cockpit displays that update in real time. Adsb promises significant improvements in air transportation system safety, capacity, and efficiency through improved communications among airplanes in the air and controllers on the ground. NASA was part of a government and industry team led by the Federal Aviation Administration, which brought Adsb to maturity. The team earned one of the most prestigious awards in aviation in 2007 for its efforts to conceptualize, develop, and implement Adsb. An important component of this work was a series of field tests with the United Parcel Service in Louisville, Kentucky, where NASA demonstrated a new capability called Airborne Precision Spacing to help relieve airport traffic congestion. This is a replica of the coveted Collier Trophy. You can see the real one in the National Air and Space Museum here in Washington. The Collier has been awarded by the National Aeronautics Association since 1911. Many of America's great aerospace pioneers have received it, including Orville Wright and Neil Armstrong. It calls attention to great achievements in improving the performance, efficiency, and safety of air and space vehicles. This is the 21st Collier in NASA's collection. So let's get to our discussion of the award-winning work. Today's arrival procedures are often very noisy, dirty, and inefficient. NASA's focus was on new automation for air and ground that not only helps relieve airport congestion, but also increases efficiency and flexibility in air traffic management, saves fuel, and reduces noise and emissions. One such capability, which is part of ADS-B, is Airborne Precision Spacing. Let's learn more about that.
New airborne capabilities will also help the airport congestion problem. High throughput at airports depends in part on achieving optimal spacing between landing aircraft. In a new concept called Airborne Precision Spacing, the air traffic controller, responsible for maximizing the landing rate, designates a lead aircraft for each capable aircraft to follow, and a target time interval to be achieved at or near the runway threshold behind the lead. With the air traffic controller's spacing goal for these two aircraft now established, pilots of the aircraft then take over, using specific maneuvers and precise speed control to accomplish the controller's assignments, with little to no further communication necessary. Using onboard computer path guidance, pilots will maneuver their aircraft within air traffic controller defined limits to close large unnecessary gaps in the arrival stream, or to create room if needed for aircraft that are resequenced for arrival or waiting to take off. Then, using computer speed guidance, pilots will make precise adjustments in speed to accurately merge behind aircraft arriving from other directions, and to fine-tune the spacing as they approach the runway. The goal is to cross the runway threshold at precisely the controller's desired interval after the preceding aircraft. In addition, the system easily accommodates the safe spacing variations required for aircraft pairs with differing wake vortex behaviors. Even though the aircraft is now under positive ground control for separation, this new procedure allows the air traffic controller to use the pilot's ability of precision flying to help increase arrival throughput and minimize delays for all aircraft assigned to that runway.
That's approved. And what about JUs? You gotta come out or
By using this new aircraft capability of airborne precision spacing, controllers at smaller airports will be able to safely handle increased traffic demand without the need to expand their ground-based air traffic control systems.
The radar technology used to track airplanes hasn't changed much in 60 years, but air traffic has increased significantly. The resulting congestion in the skies poses inconveniences for air travelers and special challenges for air traffic controllers. A new tracking technology is needed to support the volume of operations projected in the 21st century. With me to discuss the challenges and the benefits of ADSB are Robert Novia, Operations Manager with the FAA's En route and Oceanic Services Unit, currently leading the Operations Support Team for the Surveillance and Broadcast Program Services Office, and Captain Bob Hill, a retired manager of the Advanced Flight Systems Department at United Parcel Service. This question, I'm going to start with you, Robert. Can you talk to us a little bit about how arrival control is done today and how it's being improved?
Sure. And first of all, thank you, Beth. It's a pleasure to be with NASA today. Managing arrivals into a major terminal area is somewhat situational. It depends on the size of the terminal area and the traffic load. But by and large, we initially descend aircraft on published arrival procedures. And during the course of doing that, there are normally more than one transition to those arrival procedures. So by that, we mean that there could be 2 or 3 or even 4 streams of traffic that the air traffic controller has to blend into one sequence over a particular fix or location going into the terminal area. And normally, in order to do that, the normal course of business is that depending on how busy the circumstances are, the controller will have to issue radar vectors or heading changes, speed changes, altitude changes, all at increasingly lower altitudes, which magnifies the inefficiency to the operator in doing so. So the key here is to stage these aircraft more efficiently, to make earlier trajectory modifications, and by doing so, they can be smaller, maybe just minor speed adjustments. So when the controller gets these aircraft on these different streams, there's less to do to space them into the terminal area.
Now, we have a tape that was prepared by one of the partners in the Collier Trophy work. Can we roll that tape, and can you explain to us what we're seeing there?
Sure. Okay, so here we have, it shows 2 streams blending into one. So here's what I meant by different transitions in an arrival procedure where the controller has to blend those traffic streams. Now keep in mind, this is a rather sterile environment, but you can see that the last aircraft in that sequence is being radar vectored out, or a heading change, in order to get appropriate spacing.
I see a lot of dollar signs going out the tail end there.
Yeah, so that's our cute way of showing that right at that point now we're imposing a cost on the operator to get the spacing that we need. Now here is a potentially future environment where, because of minor speed adjustments we made earlier on, the aircraft would nicely fit into a gap, and this kind of mitigates that spacing problem. The controller doesn't have to issue what we call tactical measures and maneuvers to space the aircraft, and they can just fall right into the stream.
Now, this is a tough situation, obviously, for operators, Bob. How does this sort of air traffic control situation affect UPS?
Well, thank you, Beth. And on behalf of the entire industry, I'd like to thank NASA for all their work that they're doing in new technologies that will allow us to modernize the aviation. Everyone knows how important it is for NextGen to succeed, and if it wasn't for the fundamental and practical research that NASA has done, we wouldn't be in the position we are today to be able to modernize. And 2 of those technologies are ADSB and Airborne precision spacing. As far as UPS is concerned, UPS has the same problem with its major hubs as any other carrier. Congestion and delays at the hub can really harm the operation. Many of you probably aren't familiar with the UPS operation or package delivery operation, but all the aircraft come into the hub with the packages. They all have to land. The packages are then sorted, put on aircraft, and they depart back out. Louisville is a particularly important hub for UPS because it's the only hub that UPS has that all of the aircraft from all the world, so packages from all around the world, come into Louisville, they're sorted and go back out. So you can see that if any of those aircraft are delayed, the last few aircraft that are delayed, it delays the whole operation, and that could significantly affect the whole UPS operation. It could result in delayed packages all around the world. Another major problem that UPS is always looking at is the environment. How can we help the environment? I'm sure you've seen some of the articles about what UPS has done to modernize vehicles and all sorts of different alternatives to make ground vehicles more effective, burn less fuel, and make less noise and emissions. We have that same desire in the airline part of UPS. And of particular concern to UPS is noise. Because most of these operations are at night, we want to be a good neighbor, and we really want to reduce our noise. One example of that is that UPS was the first airline to comply with the lower noise standards for engine noise, and all of our aircraft were completed well ahead of the deadline. We're very proud of that.
So we have problems with scheduling and noise and fuel efficiency. What did UPS do to try to solve those problems?
Well, UPS has been involved with Adsb, like NASA, from probably the mid-90s on, and so there was a lot of work, and UPS identified this as a potential technology that could really increase the efficiency and operations at our hubs and throughout the nation. Of particular interest was some of the operational evaluations. We actually put a number of aircraft, in some cases 20 or 25, into the air at one time to test some of this technology, and those were done in 1999 and 2000. The one in 2000, actually, NASA participated with an aircraft, and there were a number of other avionics manufacturers and other participants that actually put the airborne precision spacing on the aircraft and demonstrated that it was a viable technology. Although UPS didn't really have a plan for one particular application, it did decide to further explore this by putting Adsb on all of its 7.5s and 7.6s in the early 90s. So at the same time, another project that NASA was involved with was continuous descent arrivals. The concept here is, instead of all the vectoring and altitude changes and everything that Robert talked about, what we want to do is we want to have the aircraft descend from their cruise altitude on an optimal path, both horizontally and vertically, to the runway. And there had been talk about that for a long time. Nobody had really tested the viability of that. So in 2002, 2004, there were some extensive tests that were done with UPS aircraft, and of course NASA was involved in testing this concept. We do have a slide here that shows the results of that test. On the top left, you'll see basically when we were doing these trials, how compact the flight paths were. And on the bottom one, you can see that they're all over the place. That's the difference between when you can take the airplane from altitude, put them on an optimal path, rather than all the vectoring and other things that occur in a modern environment. But the real surprise was some of the stuff on the right. There was a 30% reduction in noise and a greater than 30% reduction in emissions. That's an enormous reduction. When we're talking about a lot of the projects that are going on, people are looking for 1, 2. They think they do really well if they get 5%, but 30% reduction is just extraordinary. And that's why everybody in the industry is very excited about getting these ideas out there. And they are being used to a limited extent around the globe. And of course, the operators like it also because there is a fuel saving. It's identified there.
What's the geographic area that's covered by those the colored parts of that?
The edge of the slides are about 30, but where you see the full colored tracks and everything, that's about the last 10 miles of the flight.
So 30 miles down to 10 miles.
Mm-hmm.
And did you get any feedback from airport neighbors about whether they experienced any reduced noise?
Yes, it was noticeable, and we did get some good compliments on that. One of the funny things that happened was we were looking at some of the results, and we saw some noise spikes in some of the data that was taken at one of the sensors, and it turned out it was a barking dog. The barking dog was much louder than the aircraft.
That's pretty good.
Yes.
You had ended up having aircraft farther apart because of this. Is that right?
That's correct. That was the only negative part of this whole thing, and that's why it hasn't been more widely implemented at this point in time. To get those aircraft so that they can have the freedom to be able to fly that optimal path meant we had to put the aircraft further apart. If they're too close together, the controller has to intervene, and the controller has to take the aircraft off that optimal path. So by putting the aircraft further apart, we were able to do this particular event.
So having them farther apart is a problem because you've got a schedule to meet and packages that have to get to their destinations and customers that have to be pleased. Yes. So how did you work on that? How did you solve that?
That's the problem. And as I said, the trials that are going on today, they're only in very low density so that when you put the aircraft further apart, you don't take a real penalty. But if you try to do this in a major hub when the capacity is at the same level as the demand, you really have to, you can't do it. So we looked at putting these two technologies together, those two projects I just talked about, and adding airborne precision spacing to the aircraft. Now that's the ADS-B application. The CDA, constant descent arrival, does not require ADS-B, but to get it so it's viable in very dense operations, you really need to add the airborne precision spacing. So we put these two technologies together, and we've run a number of trials on that, and it works wonderfully. It really does. It is the solution for the future as far as how we can get all these benefits. I think that for those scientists out there, the idea is today it's basically a random system. No, it's an open loop system. The controller does some control loop, but it's really not very precise, and it's only at the end. To be able to get this so it works completely, what we need to do is schedule the aircraft a couple hundred miles from the airport. And then we control that schedule using the aircraft precision spacing. So that way the aircraft space all the way to the runway, and we're able to do this on a very repeatable basis. And one of the things you really get out of this is it turns out that you can do this in all weather. Today, the delays go down when the weather is nice because the aircraft get closer together. There's pilot involvement in the process. When we're in bad weather, we can't do that, so we end up losing capacity. When we do this, it works in all weather conditions. It's wonderful.
Now, you've brought us some animation to show how this works. Is that right?
Yes, let's go ahead and show what it would look like if we had all the aircraft at a major hub fully implemented. You'll see that the red bars in there are actually slots that the aircraft take in the schedule. The yellow bars are the ones that there's a slot that's going to be used by an aircraft coming from another direction. In other words, we're going to have a merge in the process. And the green slots are unused in this process. What we saw was the inbounds from Louisville to Louisville from the east, and now we're seeing them from the west. And you can see how precise all this looks, and there's none of that vectoring you see when you're out as a passenger day and the aircraft are flying back and forth in front of the airport.
All right, so let's scale that out a little bit. For Robert, what is the status of implementation of ADS-B, and how is the FAA integrating with all of the different government and industry organizations that are involved in this?
So the ADS-B program office under the FAA has been around since early 2006, and we've really accomplished a remarkable amount in that short period of time. We are aggressively deploying the ground infrastructure, putting ADS-B radio stations throughout the NAS. It's going to take some 800 radio stations to cover all the airspace that's currently covered by radar today. And we're also, part of the program's baseline includes the Gulf of Mexico, so we'll have surveillance for Houston Center across the Gulf of Mexico. We have 4 key sites that we hope to get implemented this year within the next 6 months. They are Louisville, Kentucky, Philadelphia, Houston Center's Gulf of Mexico, and Juneau, Alaska. Each of those sites represents a different automation platform within the FAA, so we're demonstrating that ADS-B can be integrated into the National Airspace System for the purposes of providing air traffic services. So the controller now will see targets that will be partially derived by ADS-B and radar. We're implementing new fusion trackers to integrate all the surveillance sources. And so by 2013, we expect to have the entire ground infrastructure in place, all 800 radio stations.
Great, great. Robert, Bob, thanks for being here to share with us today. We can see now why a new tracking technology is necessary to support this volume of operations that we'll have in the 21st century. In a moment, we'll take a look at airborne precision spacing and NASA's contribution to the UPS field tests with 2 NASA research scientists and our Associate Administrator for Aeronautics Research, Jaiwon Shin. But first, we want to give you an opportunity to get better acquainted with one of our 4 aeronautics research centers, the Langley Research Center in Hampton, Virginia.
Aviation pioneer Orville Wright once said, "No flying machine will ever fly from New York to Paris." Now those flights happen every day. People, goods, and services move around the globe thanks to NASA Langley Aeronautics Research. Langley engineers and technicians push the boundaries of flight ever faster and higher, leading the way in innovation and technology development. We are key to the nationwide effort to modernize the skies to meet demands for increased air travel We design technologies to make the skies safer, then take them to flight to make sure they work. And they do. Every modern aircraft relies on technology developed over the last 90 years at NASA Langley. Langley researchers are changing the shape of aircraft to come, too, making them quieter, faster, and greener. We're working to achieve supersonic passenger travel and hypersonic breakthroughs with our military partners. Nearly every U.S. military aircraft has been tested in our wind tunnels and laboratories. And when we go on to the Moon and Mars, Langley Aeronautics expertise will safely lead the way through Earth's atmosphere and those of other planets. At NASA Langley, our mission is to uplift the world through our aeronautics research and inspire innovations for a better tomorrow. NASA Langley. The future begins here.
You're watching The Leading Edge, an aeronautics research discussion program brought to you by NASA. Let me introduce our Associate Administrator for Aeronautics Research, Jaiwon Shin, who will continue our chat about an environmentally friendly solution for air traffic congestion around airports, NASA's Airborne Precision Spacing Research, with two of our research scientists, Nancy Smith and Brian Barmore. Both represent the Aeronautics Research Mission Directorate's Airspace Systems Program. Nancy is with the Human Systems Integration Division at NASA's Ames Research Center in California, and Brian is with the Crew Systems and Aviation Operations Branch at Langley. Jaiwon?
Great. Thank you, Beth, Nancy, and Brian. It's good to see you again. Thank you so much for being with us today to discuss your research. I believe our audience will appreciate how important your research is. We just heard from Robert and Bob about what real-life problems they are dealing with and what real-life benefits they have received from NASA research. So without any further ado, let's dive right into it. Let's discuss what kind of wonderful research that we've been doing, and in particular your research. To begin, I'm curious how we were recognized by National Aeronautics Association with the Collier Trophy. Let's talk about that first.
Okay. Well, I think we were recognized for the Collier Trophy because of our involvement in the activities that Bob was describing, the field trials, and I think Brian can actually speak more to some of NASA's role there. But in addition to the work that got the Collier Trophy, there's actually a larger body of NASA research on Adsb at all four of our aeronautics centers. So, in fact, the Collier Trophy award was quite substantive, and there's even more work that NASA's doing that's contributing to this. It's a key technology that NASA recognizes has real potential to improve capacity and safety in the NAS in the future. So we're very excited about working on that.
I would say there's probably been about a dozen or so ADS-B-related research projects within NASA, ranging from trying to improve safety on runways, prevent runway incursions, to increasing the throughput, particularly during bad weather, for closely spaced parallel runways, which is an important aspect of increasing the capacity of the airspace.
Brian, we've got some video from a Chicago experiment that y'all did.
So this is showing some of the work. This is one of the early trials of the Airborne Precision Spacing work. We took an early sample up to Chicago, working with a couple of our industry partners at the time. You can see one of the inside of one of the NASA research aircraft. And we took this up there. We flew it in Chicago, worked with the controllers up there, trying out, like I said, some of the early prototypes of this work. One of the interesting things You're seeing right now some of the researchers working, monitoring the data, analyzing it as it comes in. One of the interesting things that we learned by going there was we were trying a way to merge the multiple traffic streams that Robert had talked about earlier. We had a very simple approach at the time. We discovered that it really didn't look like it was going to be robust enough to use in a fully operational environment. So we've actually gone back into the lab, made some improvements on that. Some of the stuff that they're now testing at UPS has evolved out of that.
That's great. When it comes to research, I know there's nothing like doing actual flight research.
Yes.
So talk some more about how we got involved in collaboration with UPS.
Okay, well, so NASA really started probably back in, I guess it was about 30 years ago or so, back in the late 70s, looking at airborne precision spacing type of work. The main focus was on separating aircraft or keeping them far enough apart on approach to avoid the wake vortices coming from the leading aircraft. This was before the advent of Adsb, so it was using some very basic surveillance information and stuff. We have continued working it, refining it through the years. As Nancy said, in the mid to late 90s, NASA identified Adsb as being a key transitional technology. We started applying that with the, not only do you get more precise information, but you can actually get more information from the other aircraft. And so we started refining the concepts, refining the tools that we were using. So we had a pretty mature research portfolio when UPS started to do their trials in Louisville. They started talking with the FAA about wanting to actually try some of this technology out. They were aware of the work that we had done. So it was a natural partnership. They came to us, said that they wanted to use some of the work that we had been doing. We were able to see this work actually get out into the field. As we mentioned, there's nothing like having it out in the field to really learn the nuts and bolts of what you're getting. So we're getting a lot of information back that way. We're seeing things that we just can't see in a laboratory environment. And we're able to take that back into the lab and make refinements, make improvements, and continue evolving our research.
That's great. Nancy, as you mentioned earlier, we're doing far more than just the capabilities to enable ADS-B. What other wonderful things are we doing to help our valued partners like UPS or FAA?
Yeah, there's actually, as Brian was talking about the research that's gone on at Langley, I work at NASA Ames, and we have a long history of doing investigation and development of automation tools to support controllers and traffic managers in addressing their problems. One of those applications, an arrival scheduler application, is actually particularly relevant to what we've been discussing today, the work that involves the airborne precision spacing. And what we were doing at Ames, and what my group was doing at Ames, was preparing to conduct a simulation that combined airborne precision spacing, but with arrival scheduling. So we used our expertise in the arrival scheduling work and mocked up a concept, simulated a concept that used a scheduler to organize the aircraft so that when they came together at the merge, they were well positioned to pair up and to self-space. So we were getting ready to do that in 2005. We were preparing to run a human-in-the-loop simulation of this concept. And we have a researcher with our team who's been involved with the UPS activity. So we ended up making some changes to our concept so that it would emulate what was going on in Louisville. And I'll talk more about that later. But first I wanted to say a little bit about, in addition to the flight tests, some of the kind of things that we can learn and what we do in laboratory simulations as well. And I've got a couple of my colleagues from Ames, from the Aerospace Operations Lab, And we have a video clip that shows them describing what we do there.
This facility is the Airspace Operations Lab. We use it to rapidly prototype and investigate future air traffic concepts. So it's aimed at operations research with people, pilots and controllers, and with new technologies. The current air transportation system is very safe, but it's also fairly outdated. And so there is a very broad modernization effort ongoing, and there is also the plans are in place for the next generation air transportation system that is envisioned to replace the current system over the next 2 decades.
We're particularly interested in the role of humans in that kind of system, and the different roles of what the pilots might do and what they could do on the ground. So we were looking at both cockpits and air traffic controllers on ground systems and how the whole thing would work together. This research really is using an awful lot of the tools that are being talked about for next gen. It's using Adsb, satellite navigation. It's using data link communications to send up trajectories to airplanes. Next gen is very much sending up whole paths for an airplane to fly. And that's what this is doing, that the controllers are communicating with the pilots essentially via email.
So as you just heard, we have incorporated some of these advanced next-gen capabilities into our simulation lab, and we integrated a suite of that functionality to be able to test this concept that we called too wild for trajectory-oriented operations with limited delegation. I think what I'd like to show you next is another video clip that actually follows up on what Ev and Tom were saying and shows you what our lab looks like when we're actually running simulations, so you can get a little bit more of a feel for what we do. So this is our air traffic controller lab, and what you see is some controller stations, and on the back wall there's a projection of the traffic problem that the controllers are working. Now, in this case, it was the Louisville traffic problem, similar to what Bob was showing, but we were just sort of simulating one quarter of that full arrival airspace. We've got controllers here who are working at stations that are a emulation of what they actually have in the field with some advanced tools and functionality integrated in. So the weather display that you're seeing, that timeline off to the right, and the blue-colored line are all additions that are part of this emulated next-gen tool suite that the controllers are using to work this problem that we were testing. So this is, again, a little bit of an enhancement on today's displays. We have some color-coded data blocks, and again, the timeline on the left. But what the controllers are doing here, they have some aircraft, so this is our too wild simulation, they have some aircraft that were capable of self-spacing and some aircraft that were not. And they were working a problem that integrated the self-spacing and the non-self-spacing aircraft into a single arrival stream using this timeline for coordination. Now what you see here is one of our pseudo-pilots, and we have, to complete the simulation, we have some Confederate pilots who are responding to the clearances that the controllers give, and we call those guys pseudo-pilots. But what that gives us is the controller is working a rich, complex, fully responsive problem. So basically, every aircraft that's in their scope is something that responds to them. So this is a slide that shows actually the two labs that were involved in the simulation. What I was showing you earlier in the video is just some footage from our airspace operations lab, but in fact, we also had 8 commercial pilots who were test participants in this simulation study, in addition to our 4 air traffic controllers. And they were working at desktop simulators and flying the aircraft in the had some advanced displays, were able to execute the Adsb Airborne Precision Spacing clearances that they were assigned. And so I think if you could show the next slide, please. I just wanted to give you one sample of the data that we had from this simulation. And this, I guess, speaks to a point that both Bob and Robert were making earlier, that if you have self-spacing aircraft, you are going to be able to have tighter control and more precise control over the spacing interval between a lead aircraft and the aircraft that's spacing off of it. What you see here in red are, well, I guess I should explain what the plot is. What you're seeing is the error between the target interval and the actual interval that was observed for each of our aircraft in the simulation at the runway threshold. And what you see in red is how tightly the target interval was achieved when the aircraft were self-spacing. So the accuracy was within 1.5 seconds, plus or minus 5 seconds. I mean, that's really pretty remarkable. The alternative non-spacing condition had the controllers issuing speed instructions, again using tools. So this is also advanced operations, and so the controllers were responsible for maintaining the spacing, and they did a great job too, but with much more less precise control over that interval. So again, this sort of gives you a good indication of how much the spacing application can actually help.
Great, thank you, Nancy. I have been to that lab, and they are not acting up because they were being taped. They always looked that calm and professional, and but I think the benefits of your research are wild. So that name Too Wild is very fitting, I think.
Thanks.
So let's talk a little bit more about that. Out of collaboration with UPS, what kind of benefits did you get to improve Too Wild? Okay.
Well, it did change the way that we ran the simulation. We, for instance, added an arrival manager position, and in the case of this simulation, it was someone who was setting things up before the aircraft actually reached the controller sector. And at UPS, that operations is being tested as something that's done by the airline dispatcher. So that was an interesting thing for us to add to the simulation, was this third party who's actually kind of preparing the problem for the controller and the pilot. The other thing that we got out of this was that it gave us a chance to look at how a single carrier operation could mix with in an environment with a lot of other carriers that weren't conducting the same kind of operation. So it gave us a mixed equipage situation to look at that was quite interesting. The other, so I think that we got some interesting input to our simulation that definitely made it a richer problem for us to work, and hopefully provided some insights and some benefit to the merging and spacing and UPS operations as well.
Right. I think you summed up well that that's the value of partnership with our customers. Mm-hmm. So in closing, let's hear some preview. What are the next steps for NASA? What are you guys working on that will bring new capabilities that we cannot practice today?
So there's still a lot of work to be done in Louisville. Right now, the focus has been on the UPS-only operations in the middle of the night. So there needs to still be some work on extending that into daytime operations where they're having to interact with other airlines that are particularly bringing in passengers and stuff. But then moving from there, the real goal, the real impact of this work on the national airspace system is when you can start doing this at the really busy hubs, the places like Chicago, Atlanta, San Francisco, those types of places where any sort of delay or disruption that occurs ripples throughout the entire system. So we really need to start working at how you integrate those who can do this with those who have not yet equipped, who choose not to equip, a much more complicated mix of aircraft types. All that kind of stuff is going to add more difficulty to the problem. And so there's still a lot of work. We're doing stuff in the lab right now on testing new ideas on how to use this in a richer, more complex environment.
And much along the same lines, there's ongoing work at Ames developing the scheduling applications to really be able to handle these complex problems. The situation or the animation that Bob Hill showed earlier that showed the aircraft merging from multiple directions and had the red and yellow coated slots, the green slots being filled by aircraft that change color. That's a pretty challenging scheduling problem, and there's work going on right now at NASA to explore how you would manage that and also be able to support these continuous descent arrivals. So there's some interesting stuff happening that's, again, directly related to what we've been talking about today.
Great. Nancy and Brian, thanks so much. I'm looking forward to all the good stuff coming out of your research. As Robert from FAA mentioned, they are expanding ADS-B to wider ranges and more airports. So I can envision that my neighbor in the near future talking to me that, hey, my flight was aided by ADS-B today. So I'm envisioning that ADS-B becoming a household name out of your excellent research and our collaboration. So again, thank you very much, and I'm very proud of you. Thank you.
Thank you.
Thank you all. Next, we'll take some questions from our audience, but first we'd like to give you an opportunity to get acquainted with another one of our aeronautics research centers, the Dryden Flight Research Center in California. You're watching The Leading Edge, an aeronautics research discussion program brought to you by NASA. We've been discussing Automatic Dependent Surveillance Broadcast, or ADSB, and NASA's Airborne Precision Spacing Research. Our panelists today are Robert Novia of the FAA, Bob Hill representing UPS, Nancy Smith and Brian Barmore, who are with us at NASA as researchers. And we're ready to take some questions here at NASA headquarters in the audience. Do we have anyone?
I was fascinated by the earlier graphic you showed with the dollar signs blowing out the back end of the airplane. And I thought that did a nice job of demonstrating that the economic impact of NASA's research. What I'm curious about is, and to try to understand better, is then what's the next step in the process of how do we go from the research to implementation in an operational sense? What's NASA's role in that? Is that an FAA decision, or is that something the airlines voluntarily comply with?
Okay, is that directed at me? Okay. So when I was describing the initial SBS or ADSB program office objective, I was speaking mostly about just providing surveillance for ATC to provide separation services the way they do today. But really the true value with the ADSB technology is the ADSB in component, where we uplink traffic data to the cockpit. And that really opens up all kinds of opportunities to have advanced applications and to realize some of these spacing initiatives. Probably the biggest challenge we face is for an extended period of time, we're going to be in a mixed equipage environment mode. So we're in a tough spot of trying to develop operational concepts that work for when only part of the aircraft in the airspace are equipped. So that's where most of our focus is now. We have three. We call them future applications. ADSB in with the FAA work associated with that. We have three ADSB in applications that we're developing. One is an oceanic application called in-trail procedures, where two aircraft that are have less than standard oceanic separation, but they're separated by altitude. One can climb through the other if the aircraft has either the preceding or the trailing aircraft on their display in the cockpit, and through a set of procedures with air traffic control, we can actually give them a climb or descent instead of them being stuck at that altitude, in some cases over the entire Pacific Ocean for 6, 8, 10 hours at a time. So that is probably our most mature ADSB in application. We are also pursuing, initially we were calling it merging and spacing. Now we've used the term interval management to describe any ADSB in application that has to do with the spacing function. So we're sponsoring that, and we also are trying to mature and accelerate the standards for a surface application, whereby the flight crew can get indications and alerts when something slipped through the crack. You know, this is meant to give to act as a safety net to prevent a runway incursion or a last-ditched effort for the flight crew to see something. And again, this would be an ADSB in application in that air traffic control would be doing business as usual, but something went wrong, and now the flight crew, because of the uplink of ADSB information in their cockpit, they can pick up a situation unfolding and potentially avert something very serious from happening.
And if I can add from the NASA side, first of all three of those applications have been have research going on at NASA to develop them. In addition, particularly the spacing one I know about, Bob and I are on an international standards committee. And this is one of the ways where this type of information NASA can get out to the community. We're working to help set equipment standards where the airlines or the avionics manufacturers, I guess, can go and use that to develop equipment that will conform to these types of operations. So that's another good avenue where NASA can get what we've been doing out to industry to make use of.
All right, let's take another question.
Yeah, I have a question. There's no doubt in my mind that the quality of the situational awareness is enriched by the different components that you've added. My question is that as you add more components, the likelihood of getting conflicting data might increase. Is there a protocol for conflict resolution if certain sets of data indicate a certain sort of pathway, whereas another set of data, or am I not sort of, you know, as you add more components, there's going to be some likelihood either due to faulty sensor data or something or weather or whatever, that there is a sort of a conflict resolution protocol so that one thing trumps another in case there is a conflict?
I think there has been a fair amount of work on that. A couple of people in the room here were on a committee that worked on conflict management, especially when we're in normal operations and then something goes wrong. I think that is part of the whole operational procedure development and the certification and operational approval, that hopefully when we've gone through a lot of these committees and work and then actual trials, and that we end up finding most of those problems and hopefully built it into the system. The other part of it is we're not taking the controller out of the process. So the controller will be the one that will be responsible for stepping in if the controller sees something wrong or if something is not the way it should be. So I think there are multiple levels in the process. Ultimately, I think Brian talked a little bit about ultimately having aircraft self-separate a little further out, but I think that we have to go through all of these other processes, discover all those things that you talked about before we can take that final step.
There's another another area where, excuse me, conflicting information is potentially an issue, and that is for the air traffic controller. They have the conventional radar data that they're working with now, the fused radar data. And with Adsb data coming in that's much more accurate on the aircraft that are broadcasting Adsb, there's the challenge of being able to integrate the Adsb data state information about aircraft position with the non-broadcasting aircraft that are just being detected using the radar information. So there's an interesting integration challenge there, and I don't know if you're. I know that when we've conducted simulations for us, it's been interesting to try to figure out how to represent the two different types of information to the controller so that they can work with them effectively.
We have another question out of the audience.
Hi, I'm Karen, and I work with NASA Aeronautics, and because I do, I happen to know that some of our aeronautics scholarship recipients are watching today online through NASA TV, and they're going to be checking out the podcast. And I think Adsb it's such a huge issue. It's so complex. It's an incredible system. And looking, for each one of you, and in particular the NASA researchers, I suppose, seeing the video and seeing the people who are working in the simulation center, I just wondered if each one of you maybe could just briefly express what kinds of skills the researchers are employing when they're doing this kind of work. What kinds of people are working on these issues? Obviously, from the time span that Captain Hill talked about, this is an issue, and it's not an issue that's going away, and it's going to be continued to be tweaked and find solutions and then tweak those solutions again in the years to come. So what kinds of people are working on these issues, and what talents are they using? Thank you.
I would say in general, just about covers the whole spectrum of aviation experience, from having people that are involved in the operation that can put the problem down and then taking that to actually developing solutions to that problem. So I think you're going to have plenty of aeronautical engineers, plenty of operational experienced people, controllers, pilots, the whole broad spectrum of everyone that has to be involved in the solution. And I think it's a wonderful opportunity for people to take a look. But basically, you have to have obviously a fair amount of background in aviation and aeronautics to be able to do this.
Yeah, I would say, both Nancy and I have talked about a lot of this development going on in laboratories. Most of that is in simulation, so it's all computer-based. So, both of us have large teams at our centers that do software development. So that's a good avenue to get into. One of the interesting things I've learned coming into this and not actually coming from an aeronautics background, is that there really isn't any schooling set up for working these types of problems. So it actually is a nice multidisciplinary team that develops. But basically need to have the basic engineering or scientific skills, being able to logically work through the problem, set up experiments to get at what you're trying to achieve, as well as having access to the operational information and being able to bring that all together and keep the big picture in your mind is important.
And I would just add that because we're dealing with air traffic services, safety is king, and the safety analysis is quite complex, and I think it takes a very special skill set to distill that down to all the things that have to be considered in developing standards and the requirements in order to implement any system. So I think that requires a special skill set. So if you're particularly adept at knowing how to do that kind of safety analyses, I think that would be very beneficial.
All right, we've got time for one more quick question and one quick answer.
I'll make it really quick then. This is probably for Nancy. The spacing model that you showed and referred to, I guess you didn't show it, but you referred to it. If I pop up unstable convective weather in that model, I imagine from a research standpoint that makes it much more complex. Can you give us an idea of what that complexity is, or hope that research will lead to whether or not having quite the drastic effect it has now on traffic delays?
Boy, I'm not the person to take that question, but I'm a human factors researcher, and we do the studies in our lab. I could tell you that from my perspective, one of the challenges there would be being able to effectively reroute around that convective weather, and to try to be able to maintain that stream of aircraft who are self-spacing. Now, I think, and I can visualize how the controller tools could be used to do that. I know less about how it would work from the flight deck perspective, though, and you may have given this some thought.
I think there's a lot of work going in that area. Our ultimate goal is, as Nancy said, is to reroute ourselves around any thunderstorms that are there. The obvious problem, if there's thunderstorms or snowstorms on an airport, you're going to affect that airport. But there's plenty of airspace out there. So if you put together all the technologies that are being worked on, the navigation, communication, and surveillance, and the ground tools to support that, you can basically dynamically reroute the aircraft using data link and still have the aircraft be able to space off of each other, as long as they all have the information about what the other aircraft is doing. So I think it's that integration that has to occur. And I would personally like to see more work done in integration of all these technologies and that implementation of that.
Yeah, and I guess one thing that I could say to that too is that we're one of the other simulations we're working on now in our lab looks at how you could actually reroute a cluster of aircraft on the same modified trajectory. So if you had the information about where the clear path was, you could conceivably reroute all of those planes, and they could maintain their self-spacing status on that new modified routing.
All right, that's going to have to be our last question. We've had a really great discussion today, but we're out of time. On behalf of Associate Administrator Jaiwon Shin and NASA, thanks to our guests, Robert Novia of the FAA, Bob Hilb of UPS, and our two NASA researchers, Nancy Smith and Brian Barmore. You can learn more about Automatic Dependent Surveillance Broadcast, or ADSB, and NASA's research on airborne precision spacing by visiting NASA's website. We've provided copies of the charts and videos used in today's discussion and several technical papers that are detailing this research. And this is a very long URL. We'll show it to you in a minute. But if you go to www.aeronautics.nasa.gov and look for the leading edge icon, click on that, and you'll be able to find all of this information. And we do invite members of our audience to sign up for our email notices. The sign-up sheet is on the table just outside in the hallway. Thank you all for being with us, and with that, we'll call it a show.